Hey folks. So I wanted to do a video explaining the proof of this theorem, which is one of my favorite theorems from linear algebra, saying that if I give you a set S comprised of an orthogonal set of non-zero vectors, then that set S must automatically be linearly independent. Okay, so to prove this, I thought it'd be nice to start by, general strategy for proof writing, write down what you know, write down what you need to show. So what I know is that the set is orthogonal, which means if I take any ui dotted with uj, as long as I and j are different, I should get 0, right? These are mutually perpendicular vectors. And I also know that none of the vectors are the 0 vector. Cool. What do I need to show? Well, to prove something is linearly independent, I need to take an arbitrary linear combination of the u's, set it equal to 0, and say, well, the only solution is the trivial solution, right? The only way for this to happen is if all of the coefficients are 0 themselves. Okay, so now how am I going to do that? Well, to get there, I will mention some extra facts about inner products, which actually aren't new facts. If you remember that the inner product is really a special case of matrix multiplication, then all of these facts follow from the fact that, well, matrix multiplication satisfies things like distribution over addition, right? So u plus v inner product with w would be the same as u dot w plus v dot w, right? We saw distribution for matrix multiplication. Same thing should happen here. Likewise, if c is a scalar and u and w are vectors, then cu dot product with w should be the same thing as c times the inner product of u dot w. Okay, so I'm going to use these facts throughout my proof coming up, but again, these aren't new necessarily, but they'll be useful, so I want to just kind of remind you of them. Okay, so how do I start my proof? Well, to show something's linearly independent, I need to start by letting us have a linear combination c1u1 plus up to cp up, set it equal to the 0 vector, and we're going to have to argue that all the coefficients are 0. Well, to do that, I'm going to do this really nice trick, this really nice idea, which is, well, I want to leverage that inner product property that, I have sort of all this orthogonality. So I'm going to take, for simplicity, let's start with u1. I'm going to take u1, I'm going to dot product both sides, okay? And why am I doing this? Well, or why am I allowed to do this first? It's, well, the left-hand side is a vector, right? C1, U1 plus, I mean, I add all these things up, it's some vector. I can inner product that with U1. I can dot product that with U1. I can also dot product at the same time on the right. And so I should preserve that equality, right? I'm just taking the vector on the left, dot product, vector on the right, same dot product. All right, let's write it out. So I have C1, U1 plus C2, U2 plus, okay, dot, 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 CP, UP. And all of this is going to be dot product with U1. And that should equal 0, 0 vector, dot product with U1. Okay. Now, using some of the fun facts I know about matrix vector multiplication, I can distribute, right, this dot product across the summation. So I have something like C1, U1, dot product U1 plus C2, U2, dot product U1 plus, and so on, until my final term, CP, UP, dot product U1. Okay. And that equals, well, okay, on the right-hand side, I have 0 dot product U1. Well, if you take a second to think about that, I'm going to have the vector 0, 0, 0, 0, 0, right, dot product with U1. And so it doesn't really matter what U1 is, right? I'm going to get 0 on this right-hand side, right? So this for sure is just the number 0, right? The number 0, not the vector 0, the number 0. Okay, well, let's continue. I can continue simplifying on the left, and you might notice on the left, again, I can pull out those scalars, and I'll get C1 times U1 dot U1 plus C2 times U2 dot U1. Aha, maybe you're starting to see some interesting things develop here. Finally, CP times UP dot U1. Again, that equals the number 0. But now I can use that critical assumption that these are orthogonal vectors. So U1, U2 are orthogonal by assumption. So this inner product is 0. In fact, UP dot U1 is 0. And in fact, all the terms in here are all going to be 0. The only one that's not 0, right, is this first one. Okay, because if I do a vector dot product itself, that's really like the length, right? This is like really the length squared. And because the vectors are non-zero, this has to be non-zero. So simplifying all this down, right? At the end, what I really get is C1 times U1 dot U1. All the other terms on the left-hand side go to 0, but this equals 0. And now the critical observation is that since this is not 0, it must be the case that C1 itself must be 0, right? Because otherwise, how am I going to multiply these two numbers to get 0 on the right-hand side? So it must be that the coefficient C1 was 0. Well, that's C1, but notice, if I repeat what I just did for any other of the UNs, right? So U2, U3, U4, the same exact thing will happen, and I'll deduce that what all the other C coefficients are also 0. Okay, so the nice thing about this is I could repeat this process for each UI to show every single CI, must be 0. And so combining all of these, right, it must be the case that in fact all C's, C1 all the way up to CP, are all 0. And that's what I needed to show to convince myself that this set was linearly independent. Okay. I hope you thought this proof was interesting. I really like this. I think it's really nice when suddenly all these terms go to 0. You're just left with one term left on the left-hand side. It's a very nice idea. Okay. If you have any questions, let me know.